Hello everyone, welcome to the Mechanism channel. Today's topic is the difference between ASME and ISO GPS GD&T standards. The ASME, which stands for the American Society of Mechanical Engineers, and ISO GPS, the International Organization for Standardization, Geometrical Product Specifications, are two widely used standards for geometric dimensioning and tolerancing, or GD&T. While both systems aim to ensure part quality, compatibility, and interchangeability, there are key differences between the ASME Y19.5 standard and ISO GPS. These differences stem from their development histories, industry served, and technical detail. Let's dive into the key differences between ASME and ISO GPS. 1. Scope and global reach. ASME Y14.5 is primarily used in North America, including the United States, Canada, and some companies in other regions. Developed by ASME, it has a strong presence in sectors such as aerospace, automotive, defense, and general manufacturing. It emphasizes clear and unambiguous communication of tolerances on engineering drawings. On the other hand, ISO GPS is internationally adopted across Europe, Asia, and many other regions globally. It focuses on harmonizing global standards to facilitate international trade and manufacturing. ISO GPS covers a broader range of topics beyond just geometric tolerances, including surface texture and material properties. 2. Tolerancing philosophy. ASME uses a more functional approach to tolerancing. It tends to focus on the functionality of parts in relation to their final assembly. ASME emphasizes a single system that is easier to interpret for manufacturing, assembly, and inspection. Material condition. Modifiers like MMC, LMC, and RFS are used frequently to control tolerances. In contrast, ISO GPS takes a more mathematical, metrological approach. It provides detailed specifications on how features should be measured and controlled. The ISO GPS system is made up of many interrelated standards, which can provide more precise control but add complexity. There is less emphasis on material condition modifiers compared to ASME. ISO uses more complex symbology and definitions for feature sizes. 3. Feature control frames, or FCF differences. ASME Y40.5 typically uses a simplified feature control frame structure with clear placement of GD&T symbols and values. Focuses on basic dimensions with tolerances applied at key points to ensure the functionality of features in relation to datums. In contrast, ISO tends to use additional symbology and specifications in feature control frames, making them slightly more complex but more detailed in interpretation. For example, ISO allows direct tolerance on angles, and additional symbols are used to differentiate between maximum and least material conditions. Datums and datum systems. ASME. Datum precedence is strictly controlled. Datums are labeled as primary, secondary, and tertiary, with specific importance attached to each. ASME requires all datum references to be fully defined and placed in a clear hierarchical order. ISO GPS. ISO allows for more flexibility in datum structure. It introduces concepts like datum targets, which are specific points, lines, or areas used as datums. ISO standards permit the use of compound datums more readily, meaning two or more datum features can act together. The use of free state datum in ISO accommodates parts that deform, such as thin-walled or flexible parts, modifiers, and symbols. ASME. ASME uses fewer symbols and has a more straightforward interpretation of modifiers like MMC, LMC, and RFS. Positional tolerance is often given with material condition modifiers to optimize part production by allowing more tolerance when parts are closer to their maximum or minimum material states. ISO GPA. ISO uses more extensive symbology, offering more specific controls, especially for features such as envelopes of sizes and skin models, which are the theoretical boundary surfaces of a part. ISO also differentiates more types of material conditions beyond MMC and LMC, including maximum inscribed circles or spheres and minimum circumscribed shapes. Profile tolerance differences. ASME, profile of a line, and profile of a surface are commonly used, controlling either a line or surface's deviation within a uniform boundary. ASME applies these tolerances in a straightforward manner for both two-dimensional and three-dimensional surfaces. ISO GPS. ISO differentiates between unilateral, bilateral, and non-uniform profile tolerances, offering more detailed control over the form and distribution of tolerances. The ISO profile tolerance is more mathematically defined with additional notations for freeform surfaces and more complex geometries. 7. Interpretation and complexity. ASME is typically considered easier to learn and apply in comparison to ISO, as it uses fewer symbols and has more straightforward rules. It's often chosen for industries requiring rapid communication between engineering and production teams. On the other hand, ISO GPS is considered more complex and detailed, which makes it suitable for precision industries, but can be harder to implement without advanced knowledge. The measurement and inspection process in ISO GPS is more rigorously defined, sometimes requiring sophisticated metrological equipment. Standards. Integration. ASME. Mostly contained within one major standard, ASME Y14.5, with supplemental standards for specific topics like surface roughness, ASME B46.1, ISO GPS. Many different standards make up the ISO GPS system. For example, ISO 1101 for tolerances, ISO 54, 59 for datum systems, ISO 14405 for size tolerances, and each governs different aspects of the tolerancing process. Summary of key differences. Conclusion. Both ASME Y14.5 and ISO GPS are robust systems for controlling part geometry, but ASME is simpler and more focused on practical, functional dimensions, whereas ISO GPS is more precise and mathematically rigorous, allowing for greater flexibility and detail in complex engineering tasks. The choice of system often depends on regional preferences, industry requirements, and the specific complexity of the parts being designed. Thanks for watching. Please like, share, and subscribe. Happy learning.